So we've also done 9 installations in the past year, so it continues to be a fairly popular technology. And the new news in inlet fogging is that GE has recently approved the use of at least MEFOG systems on their gas turbines. So they gave us this letter showing that they approved of the technology. They have no objections to the use of MEFOG systems on GE gas turbines, provided that the applicable TILs are followed. Now, there were a lot of fogging-related TILs issued for 7FA gas turbines, which you all probably know had a little bit of a problem with the inlet blading. Those TILs specifically apply to the F-series turbines and not to the EA turbines. So to my knowledge, there are no TILs that specifically deal with fogging for 7EA gas turbines. The technology is pretty simple and straightforward. It's basically a high-pressure pump skid. We use demineralized water. That's to avoid fouling the compressor blades if water gets in there. There's high-pressure feed lines that go to a nozzle array up in the inlet filter house. And the fog is injected into the airstream and it evaporates as it's carried with the airstream to the compressor inlet. So for evaporative cooling fogging, where people are concerned, mostly OEMs can be concerned about fog entering the compressor. In that case, we inject just enough fog to fully saturate the air, and we try to give it maximum evaporation time so when it comes to the inlet, it's fully evaporated. But for overspray fogging, we'll actually typically do a slightly different installation. We'll put the nozzles very close to the compressor. Now, this might be evaporative cooling and overspray. In fact, with nozzles located here, there will be some evaporative cooling of the air before it enters a compressor. But most of the droplets will fail to evaporate and will go inside the compressor. So the benefit there is that the droplets evaporate inside the compressor, lower the temperature in each compressor stage, and that reduces the amount of work that the compressor is consuming. So you get a pretty good power boost. Overspray produces about 5 to 10% for every 1% of the air mass flow of water injected. So those are the 2 simple applications of inlet fogging. And this shows specifically for a 70EA turbine, 7121EA, whoops. Not used to this trigger down here. Starting at 100 degrees Fahrenheit and cooling 40 degrees, and I picked that number because that's about 1% of water spray. So to cool from 100 to 60, you had to spray about 1% of the air mass flow as liquid water. In this case, it's evaporating before the compressor, cooling the inlet air, and increasing the output of the gas turbine. The next 1%, for a total of 2% now, becomes overspray. It can't evaporate before the compressor because the air is fully saturated here. And that gives us an additional power boost of about 5 megawatts in this case. So this was 12 megawatts for cooling for 1%. But for 1% of overspray, it's only about 5 megawatts. So the boost from evaporative cooling per pound of water is much bigger than from overspray fogging. But of course, the advantage of overspray fogging is if you do enough of it, you can get all the way from 70 to 93 megawatts, which is quite a large boost. We use this concept called evaporative cooling degree hours. It's basically the number of hours in a year that you could cool 1 degree Celsius, in this case. I think this is Celsius. Yeah. So what we've done is listed all these cities around the world to show that there's considerable possibility for evaporative cooling even in cool northern climates like Geneva. You can still do 10,000 hours of cooling. Compared to Cairo, it's only a quarter as much, or to Delhi or Riyadh, it's about 1/9 of what you could do in Riyadh. But there's still significant potential for evaporative cooling. So it seems to be a common perception amongst gas turbine operators that are in humid areas that evaporative cooling wouldn't really work for them, but we found that's not the case. So we have installations in Bangkok and Ho Chi Minh City, Malaysia, near Singapore, many different environments that have fairly low cooling potential, but still the economics is quite good. We also take this data and I didn't bring an example of it today, but we can make a report for a particular site that says how much evaporative cooling hours you can do, how many megawatt hours that will produce, how much water you use, how much extra electricity you'll use for the fog pumps, etc. So we can do a full month-by-month report of how many megawatt hours a particular site can make. That comes in real handy for economic evaluations. This compares different cooling technologies. First, equipment and installation cost. We're comparing chillers, evaporative coolers, traditional media type evaporative coolers, and inlet fogging with overspray. So chillers are quite expensive, fogging is quite cheap. Operating costs, again, chillers are high, fogging is low. Maintenance costs, same thing. Power boost, if you do a lot of overspray fogging or wet compression, you can actually approach the power boost that you would get from a chiller, but of course for a fraction of the first cost and operating costs. And the efficiency or net heat rate, I think, might be slightly better with fogging and overspray, although you actually also should calculate the cost of the water, which becomes non-trivial when you're injecting 3% of the air mass flow as water. So economically, probably in terms of efficiency, if you take water into account, it's kind of a wash between those two. And the effect of ambient humidity, again, people tend to think that fogging is highly affected by humidity, as evaporative cooling is. But if you do overspray fogging, you can still get a very large power boost in a humid environment. This shows a typical nozzle array. These are high-pressure feed lines coming from, in this case, from distinct high-pressure pumps. So there's 6 high-pressure pumps on the ground below the turbine inlet. These are high-pressure lines coming up. So one of these feed lines will feed multiple nozzle lines, and we try to spread them out. So the first stage might be one on the top and one on the bottom and one in the middle and another one in the middle. So they're kind of overlapping staging. That's to avoid uneven cooling at the compressor inlet. And they're staged so that the system can automatically, if the operator chooses, it can automatically follow the weather. So if it gets hotter and drier, it'll inject more fog and do more cooling. If it gets humider, it'll back off on the amount of fog. This shows a typical fog nozzle. This is an impaction pin nozzle, which is our specialty. It has a 150 micron orifice and this impaction pin. So the water flows through the stainless steel tube, up through a nozzle adapter. There's an O-ring seal, a last chance filter. It comes out of the orifice in the center of that nozzle and breaks apart into fine spray. It's all, there's safety wires to protect against FOD. These are all TIG welded components. So it's quite safe to put it in the inlet duct. Comparing droplet sizes is probably the single most important factor in evaporative cooling with fogging, or overspray with fogging, is droplet size. So smaller droplet size means it evaporates faster, it produces more cooling more quickly, you use less water because you have less fallout. There are many, many advantages to it. This just shows an example of how small a fog droplet can be. That's a 20 micron droplet and a 100 micron strand of human hair. Each nozzle is actually producing billions of droplets per second.